In the sixth and final video of this series, we'll use the existing simulation case to set up a parametric study. The Fluent parametric workflow enables running multiple simulations with the same geometry at varied operating conditions. This is useful to investigate the rocket performance over different speeds or altitudes with different atmospheric pressures. It is important to note that only simulation case inputs can be parameterized within Fluent itself. To iterate through small changes in geometry, such as fin position or fuselage curvature, workbench integration and advanced CAD knowledge is required, which is beyond the scope of this video series. Starting with the initial mesh from our Mach 2 simulation, we'll do a parametric study by selecting the Parametric tab and pressing Initialize to create the project workflow, and save it in the working folder. When running a parametric study, be aware that there is frequent reading and writing of case files, which is sped up in this video accordingly. A parametric setup requires both input and output parameters to be specified. To do this, we create named expressions to be used as inputs. An expression to specify the flight Mach number is created and enabled as an input parameter in the lower left checkbox. Now in the Parametric Study tab, we can see the flight Mach number specified as a variable input. The input expression is then selected in the Boundary Conditions pane, and additional expressions can be created for other variable boundary inputs, including the atmospheric pressure and temperature, by selecting New Input Parameter in the dropdown. Finally, ensure that the input expressions are set for all boundaries where they apply. In this case, we'll make sure our input expressions are set for the far-field inlet and outlet boundary conditions. To set the output parameters, we can select existing reports, such as the already defined drag force on the rocket, or create a new monitor report, selecting the option to set as an output parameter in the report definition pane. Since we've added parameters, the simulation needs updating. As the base case is the currently selected setup, we can select Update Current to run the simulation. As the simulation runs, the console shows the standard running outputs, and graphics are displayed for residuals and monitors. Once complete, any remaining graphics objects are generated and the simulation data is saved. Opening the Parametric tab, we can see the output parameters are updated in the table for the current design point. Design points can be added to the Parametric Study table and the input parameters modified to represent different flight conditions. For this study, we'll increase the Mach number to see the change in drag at different speeds while maintaining the same altitude. Enabling the Write Data option will retain the simulation data if you wish to reopen a specific case for inspection later. To run the added design point, set it as the current case and select Update Current. In the background, Fluent will create a new case file, update the modified input values, initialize, and run the simulation for the selected design point. For this design point, residual limits are not met, and the residual's progress flatlines. You could pause the simulation and adjust the solver settings. However, instead, we'll let the run complete and check the monitors. Even though residual convergence was not met, mass flow in and out of the domain is computed, and we find that the mass flow is conserved. The monitors are also invariant, so the results are valid. To complete the parametric study, we'll continue adding design points representing a flight speed envelope from Mach 1.5 to Mach 3. By selecting Update All, Fluent will run all the design points where the status is Needs Updating. Depending on the computing load, you can run the required simulations either sequentially or concurrently. Once complete, the output parameters can be compared in the design point table. To view graphically, you can also create a comparison plot for the desired variables. Here, we'll plot the Mach number against the rocket drag force. Here, we see a doubling back of the plot line because the data is plotted sequentially for the design points run. However, the design point table data can be exported into CSV format and be manipulated further outside of Fluent by selecting Export in the Design Point tab. And finally, we'll briefly look at how to use the same simulation case setup for different geometries. Here, I've reloaded the original base simulation case. We've exited the parametric project, as different geometries cannot be included in a single parametric study. However, if you want to reuse an existing case setup with a new meshed geometry, use File, Read, Mesh, and select Discard Data, Replace Mesh in order to keep the simulation settings, but use a new mesh. Here, I'll load the mesh from a geometry where I added air brakes to the rocket. Once the case loads, default boundary conditions will be added to any new surface names. In this case, the only additional surface is for the air brakes. It is important to keep the same name selections for common surfaces between the geometries. Since the naming is consistent, the inlet and outlet boundary conditions remain. Finally, ensure to add the new surfaces to the drag monitor to account for the additional drag of the air brakes. Then make sure to save the new case with a unique name as to not override previous cases, then initialize and run. Once the simulation is complete, we can post-process the results as usual. With the existing graphics objects, the shock structure caused by the air brakes is evident, and the new drag force can be computed in the flux report and compared to the original design.